Okay, so thanks to everyone for being here. Okay, this is the title of my talk. What I'm actually going to do, I'm also going to talk about this, but what I'm going to do is try to answer this question. So how many dimensions are there at the Planck scale? Which is a topic that has been touched already during this conference, and actually some of my answers were spoiled by Joao, but that was agreed on, so that's fine. So what I'm going to do is to discuss a few. So if we want to answer this question, we first have to decide what is the notion of dimensionality that we want to use. Here I will discuss a few. So one is spectral dimension, that you might have heard of already. The other one is Hausdorff dimension of momentum space that was mentioned by Joao before. And then I'm going to talk about another notion that I call quantum vacuum dimension. That is then related to the actual title of my talk. Okay, so let's go with the first thing. So spectral dimension. So spectral dimension is the most popular way that quantum gravity researchers use when they want to discuss about dimensions at the Planck scale. Why is it? So here, let me first say what is spectral dimension in the classical case, so no quantum gravity. In this case, we want to study the properties of some Riemannian manifold, and we do that via heat diffusion equation. This one here, where so this is a diffusion process from a point xi0 to point xi during a time s. Given the diffusion process, we can define the return probability density, which is the probability density of the particle that is undergoing diffusion to come back to the point where it starts from. This is just the definition. Then by evaluating the spectrum of the heat kernel here, we find out that the return probability density can be written in this way. So it's just the sum over the eigenvalues of the Laplacian. So the delta here is, of course, the Laplacian defined on the manifold whose properties we want to study. Let me note only that from here, you see that if we look at the return probability density for small values of the time s, what we are going to probe is mostly the higher eigenvalues. And this is useful for later. So here is just to show you that actually this return probability density, it is related to the geometrical properties of the manifold. In fact, we can, via the heat trace expansion of this, we can expand the return probability density in these ways. And so this is the diffusion time, and these are coefficients. Here are just the first few ones. And you see that they are related to the geometrical quantities that you can define over the manifold. And indeed, from the return probability density, you can define this notion of spectral dimension that is just only tells you how the return probability density is varying with respect to the diffusion time s. And what it is found, and this is just standard, is that if we look at a smooth Riemannian manifold, then if the manifold is flat and is d-dimensional, d small d, then this spectral dimension is going to be constantly equal to the dimension of the manifold. On the other hand, on a more general manifold, so a curved manifold, we have that the spectral dimension is varying, it's not a constant. In particular, for small values of the diffusion time, the dimension will match the actual dimension of the manifold. And while for very large diffusion times, it will go to 0. And the way it goes from the value of d to the value of 0 depends on the properties of the manifold, such as the curvature and so on. So this is small values means small values of S means that we are probing the manifold on small scales, and that's why we get the same result as the flat space case, because it's locally we can approximate it as flat. While for large values of S, we are probing the large scales. I guess so. Yeah. Okay, so this is classical, but people working in quantum gravity have been trying to extend this concept to non-smooth Riemannian manifolds, so to whatever they assume that is the structure of space-time at at Planckian scales. And the way they have done it is to consider a fictitious diffusion process on the whole of space-time. So the whole of space-time is the new manifold on which we consider the heat diffusion process. And then there is, of course, a fictitious time that is the diffusion time. So on one hand, the space-time, on the other hand, is fictitious time. And moreover, they have to consider a Euclidean version of space-time, of course, because this diffusion process is defined on a Euclidean manifold. Then it is still true that on the infrared, the diffusion process is probing the global geometries of the manifold. So in the infrared, we expect this spectral dimension to actually give the same results that we would expect on a smooth manifold. On the other hand, in the far UV, so for the diffusion time going to 0, we expect to be probing the quantum regime. And indeed, it is found that in every model of quantum gravity has its own way to compute the actual value of this spectral dimension and its behavior in the far UV. But what is the general result is that on very small scales, the dimension does not match anymore the classical dimension of the space-time. So there is a running not only in the infrared, but also in the UV. This is just a plot taken from this paper to show you what's going on. So this is for three-dimensional CDT. It's a simulation. So in this case, they can actually simulate the diffusion process on the space-time. And you see that in the infrared, you get that. So this small scale here, it's small compared to macroscopic scale, but it's big compared to quantum gravity scale. So it's a mesoscopic scale, let's say. So on the mesoscopic scale, we have that they get 3 dimensions, which is what they started from. In the far infrared, the dimension goes to 0, which is what we were expecting. But then you zoom in here, and this is what you get, that the dimension is running from 3 down to somewhere close to 2. And this is the regime where we are probing the quantum properties of spacetime. And in this sense, you can say that for this model of 3-dimensional CDT, spacetime is becoming 2-dimensional in the UV. You have heard something about this already in the past days, but I'm going to repeat to also fix notation and so on. What happens is that you have all these models of quantum gravity. Each one has its own way to compute the spectral dimension. But from the spectral dimension, once you have it, you can deduce something about other things of your model. For example, about what is the Laplacian of your model, not in all cases we do have Laplacians for a quantum gravity theory, but you can actually go from the spectral dimension to the Laplacian and back. We have seen that the definition depends on the Laplacian. And in particular, you can show that a running of the spectral dimension in the UV is associated to a deformation of the dispersion relation. So if I write the dispersion relation in this way, so this would be just k square in the standard case, but it can be any function in principle. Then you get a deformed Laplacian, of course, and then this enters in your heat diffusion equation here. So that the return probability is written in this way. And here is where you have normally you have where the mass shell enters. And the spectral dimension can be written in this way here. This was the relation between the spectral dimension and the equation of motion was discussed in this paper from 2011. So the claim is that a running of the spectral dimension can be seen as a theory on a theory with a deformed Laplacian. This is one example. That is the example that Joao was considering, and that we have seen that is very important for cosmology. So if I take this dispersion relation, for example, here gamma is some parameter telling me how the dispersion relation is modified. Lambda is the scale where the modification becomes important. Then I get the general result that the spectral dimension in the UV is this one. And in particular, you can see that for gamma equal 2, we get the running to 2 dimensions, which is what Joao focused on. But more in general, you get running. So this is the infrared value of the spectral dimension, which is 4. And these are 2 lines, one for gamma equal 1 and one for gamma equal 2, and you see a running to different values of the dimension. Okay. So this is spectral dimension that is good because can be applied to many models of quantum gravity. It's one of the few things that can be actually computed in most models of quantum gravity. But I would say that it's not extremely physical as a notion of dimensionality. So, for example, because we are considering a Euclidean version of the theory, so it's not the actual theory, it's a Euclidean version of the theory, then it's not clear what is this fictitious diffusion process that we are considering, what is this diffusion time that we are considering. So let's see if we can find some other notion of dimensionality that makes a bit more sense from a physical and intuitive point of view. So in order to do this, so this is one first option, dimensionality of momentum space. So to go to the dimensionality of momentum space, we can actually start from one observation, which is, so this is the definition of the spectral dimension that I have shown before. Here is where the dispersion relation enters, in these 3 places. But these are integrals, and you can actually change variables in the integral. You're not doing anything. It's just a mathematical manipulation. And you can do it in such a way that the dispersion relation looks standard, and all the non-triviality of the theory goes into the momentum space measure here and here. Now it's maybe an easier model to look at, because you look at the dimensionality of the measure in the momentum space, and you can directly guess what is the dimensionality of the theory that you are considering. So let's look at one example. Again, the dispersion relation that we like because of the cosmological implications. We can change variable in the standard way, and here is how the measure is modified. This is in the UV limit, of course, which is what we are interested in. And from here, we just simply read the dimensionality of the measure. And it turns out that this is the dimensionality of the Hausdorff dimension of the momentum space that we are considering. So here it's 3 because I'm considering a 3 plus 1 case to begin with. And this is actually the exactly same expression that we had found for the UV value of the spectral dimension for the same model. And indeed, for example, for gamma equal 2, we get again a two-dimensional measure. So we are matching what we had found for the spectral dimension, and no surprise because we just changed variables in the integrals. And here is one more general example. So here is a dispersion relation where not only we have higher powers of the spatial part of the momentum, but we also have higher powers of the energy. And again, we look at the return probability. We change variables in the UV in this way here. And we get a probability density that is what we would have on a classical theory, apart from the fact that we have a deformed measure, which is all of this thing here. And again, from all of this, you can just read out the Hausdorff dimension of momentum space, and it turns out to be this. So it depends both on the higher powers you have in the energy sector and in the spatial momentum sector. And this is not the end of the story, because actually within this framework we can show that you can actually have dimensional reduction not only for Lorentz violating theories, so this is clearly a Lorentz violating theory, but you can actually implement the dimensional reduction in theories that are relativistic, even though they deform Lorentz symmetries. And so this is one example. So the way you build a relativistic theory when you have a modified dispersion relation is to accordingly deform the measure of your theory so that the two things together are invariant under some deformed Lorentz transformations. And this is one famous case, the curved momentum space with the de Sitter metric. So this is the metric of the on the momentum space. So this is not space-time. Let's not get confused. And from this, we just write down the measure as we would write down the covariant measure in a curved space-time. So it's just the determinant of the metric, and this is the measure. And then the relativistic symmetries of this theory are just the isometries of the de Sitter group, because this is just a de Sitter momentum space. And of course, we also have to write accordingly a dispersion relation, and it turns out that a dispersion relation that is actually a famous one, because comes originally from the literature on the kappa Poincaré group. It's this one here. So this is actually for who of you knows about what I'm saying, it's the Casimir of the kappa Poincaré algebra. This is invariant under the isometries defined by this metric here. And more in general, we can consider any function of this Casimir to be the Laplacian of the theory we want to study. And this theory is going to be a relativistic theory. You can easily check by actually transforming all the quantities in here that the return probability density is now it's an invariant quantity, and it is written in this way. So we have a deformed dispersion relation and a deformed measure. We have the two things together, but still we can perform again a change of variables again here at this level. So that the dispersion relation becomes trivial and the measure gets even more deformed than what it was already. So in the UV, this is the change of variable that you do. Okay, this it's not interesting to look too much into the details. And this is the final version of the probability, of the return probability density that you get. So it's the standard one with some deform measure here. And again, we can just from here read out the dimensionality of the momentum space of this model. And this is what we get. So again, gamma is the power appearing here, so it's this one. And D is the number of spatial dimensions we started from. And so this is one example of a theory with of a relativistic theory that has running of that has a running dimension at the Planck scale. And in particular, we see that for gamma equal 2, again, we can get running to 2 dimensions. So it is not true that in general that if you have a running dimensional reduction in the UV, you need to break Lorentz symmetries. You can just deform them and still have a relativistic theory. So how much time do I have more? Okay, perfect. Okay, so this is just to put together what we know until now. So I have told you that the spectral dimension is the running of the spectral dimension is a very common feature of quantum gravity theories. It appears in several occasions. Here are just a few instances where you can find it, and the usual, the most common value for this UV dimension is 2, and we have seen in Joao's talk that actually this running to 2 dimension is very special from the point of view of cosmology. Okay, but I'm still not very happy about the way we are characterizing the dimensionality of at the Planck scale. So first of all, we were still relying on some Euclidean version of the theory, and okay, the spectral dimension has this problem of this diffusion, fictitious diffusion problem, and still we don't know what we would like to actually measure directly the dimensionality of space-time. So we would like to have some more direct thing. And this is where I go to the title of my talk, because I want to claim that actually one way to measure dimensionality is to look at the vacuum fluctuations of the theory. Okay, let's see. First of all, let's see how you compute these vacuum fluctuations in a theory where the dispersion relation is trivial and the measure is deformed. So it's in the variables where all the information about dimensionality is already contained in the measure of the momentum space, because I want to see if this information encoded in the measure, it's actually something real or it's something that I'm just making up. Okay, so we want to quantize a scalar field that has these properties here. So where I need to start from the covariant on shell measure. This is just the standard step that you do when you want to do quantization of a scalar field. The covariant on shell measure can be written in this way. So this is the measure that appears here, but with the energy that is on shell. So this EP is not the Planck energy, it's the on-shell energy. Let's not get confused. And this is the covariant on-shell measure. In the standard 3+1 dimensional case with the trivial dispersion relation, it's the well-known, it takes this well-known form here. Okay, then we use, but this is the standard one, but this can be general, this can be anything. then we expand our scalar field in the usual way in terms of creation and annihilation operators, with the difference that here there is the covariant on shell measure that could be deformed. And the assumption that we have to make, but which turns out to be to give a consistent framework, is that one particle states satisfy this conservation relation here, which would be the standard one. So this one, if so this is a delta function associated to a deformed to the measure mu bar. So it's just the delta function that satisfies this relation when you integrate it together with the correct measure. And this is just the standard result in the standard case. So it just gives you what you already know from quantization of a scalar field. It's just that if the measure is different, then you get a different delta function because it still has to satisfy this relation, the definition of the delta function. And actually, I want to comment on whether this is a reasonable assumption also in theories that are in DSR theories, so in relativistic theories with deformed deformed Lorentz transformations. So maybe this slide is going to be more for people who know already something about it. But if I want to do this in the context of kappa Poincare coordinates, so it's basically the de Sitter momentum space that I have discussed already before. So this is the measure that is the same that you have seen in a few slides ago, and this is the Casimir that is the same that you have seen already. Then what is the problem at this level? Is that we know that for the theory to be relativistic, we also have to add another modification to the theory, which is that the conservation rule of momenta in interactions are deformed. And this means that also the conservation rule appearing for the two-point function has to be deformed, and in particular, the delta has to contain has to be a delta of the deformed sum of the momenta. And for the kappa Poincare model, the deformed sum takes this form here. And the fact that you have to do this was shown very nicely by Michele in a paper from 2011. So for details, you can go there and have a look. So in principle, it seems that this assumption here, it's not an assumption that you can do if you want to keep relativistic invariance of the theory. But that's actually not the case. And what is interesting is that it's not the case only if you restrict yourself to the two-point function. Because only in that case, when you also take into account the fact that your field has to be on shell, well, because you're quantizing an on-shell field, then you can rewrite the delta, this one here, so that at the end you are left with the standard delta with some energy factors in front of it. And what you find is that the energy factors in front of it are exactly the ones that you get if you explicitly write down this delta function here, taking into account that is the delta function associated to a deformed measure. So for the scopes of computing the two-point function, you don't care about the fact that you have a deformed sum rule in so it's valid in this base? No, it's valid in general. If you go on shell, so it's valid also if you do it in, for example, the linearizing coordinates that are the ones that would match within this framework. So the ones where the Casimir is trivial and everything is in the measure. It's just a matter of going on shell and doing the computation. Okay. Okay, so we have seen how to do the quantization, how to compute the two-point function, and now we want to compute the power spectrum of the perturbations, which is something that we can measure. That is something that we can measure, and that is measured in cosmology, as Joao showed. So how do we do it? So for example, in cosmology, the power spectrum of cosmology, which is the power spectrum that we want to be scale invariant in that case, is defined in this way here. This is the expectation value of the curvature perturbation. The curvature perturbation is related to the scalar field in this way. So there is a dimensionful constant, which is the Planck length in front of it. So this is what we want to compute. To compute that, it is easy to start. It is easier to start from a covariant power spectrum that is defined in this way here, and this is the deformed measure of our theory. And the two spectra, just by comparing the two things and putting all the dimensionful constants at the right place, they are related in this way. And this is a general relation. It doesn't depend on the specific measure that we are considering. It's general. Here, mu bar, it's just what appears here if you write the measure in this way. So it is the relation depends on the measure, meaning that the measure appears, but the way it depends on the measure, it's always the same. So this is general. And another thing that is another general result that is very useful is that this covariant spectrum here is always one, regardless of the measure, regardless of the theory that we are considering. So then it's very easy to compute the actual power spectrum of the perturbations, starting just looking at the measure, because then this is one, and this is you just have to put in here the measure. So we can do it. So let's consider a generic DH dimensional measure. A covariant measure, yeah, which is the one that we are using. And then only by dimensional arguments we find out that this is the way that the way you generically write a DH dimensional measure. So here, this is lambda is the scale. It's the quantum gravity scale, the same that has appeared before. This is, yeah, and everything else was already defined. In the standard case, you get the standard answer just to check. Okay, then we can use this general measure in the power spectrum, and this is what we get. So in the next slide is written more clearly, putting together all the coefficients. So the power spectrum so this is now true for a general measure. Yeah, I'm done. For in the H dimensions, so it's related to the Planck length, the quantum gravity length, the dimension, the spatial dimension of space-time at the classical level, and then yeah, and then the P that is the one appearing here. So first of all, one nice thing is that when the dimension of the momentum space goes to 2, the power spectrum is scale invariant, which is what Joao was talking about. So we recover the scale invariance, and this is nice. Plus, we see here how this hierarchy between the Planck scale and the quantum gravity scale appears. So it just comes from this, just naturally. And this is okay, already one good result, but we can stay here at this level, at the generic DH level, and compare with the way that in which usually the power spectrum is parameterized by cosmologists, for example, which is this one. So here is the amplitude, and here is the spectral index. So just by comparing this with this, we get that there is always a relation, a direct relation between the the spectral dimension, and the dimensionality of momentum space. So now we have actually a physical notion of dimension, because you can always the power spectrum of a scalar field is something that you can actually measure. So this is I would say a physical notion of dimensionality. And I have only one last slide where I want to comment on the fact that until now we have been talking about, so this notion of dimensionality here seems to apply only to the momentum space. But we would like to be able to say also something about what's happening to the space-time counterpart. So is this just running of dimensions in momentum space, or is something what's happening to the space-time in the meanwhile? They are related. We want to understand. And this is what happens. So it happens that all the quantization procedure that I have described before is consistent with equal time commutation relations of this kind here, with the deformed measure here. And just by looking at this and asking that this is actually some delta function in space-time, we can write down what would be a reasonable candidate for a space-time delta function, which is this one. From the delta function, just by asking that the delta function is related to the measure in space-time by the usual definition, you can write down the measure also in space-time, and in particular, what is nice is that it turns out that the delta function associated to the deformed measure is related in this way to the delta function associated to standard spacetime. So basically what happens is, it happens that the spacetime is behaving, so this is, the spatial delta only. The spatial delta is behaving as a standard delta in dh-1 dimensions. So it seems that also on the spacetime side we are having a dimensional reduction, and of the same kind that we had on the momentum space. So this is the spatial part, this is dh-1, and then you have one time dimension, so you end up with dh dimensions in spacetime. And the last thing, what is very nice, is that on the spacetime side, you have that the separation between time and space remains even when you do the dimensional reduction. This is not something that happens on the momentum side. On the momentum side, when you do the dimensional reduction, energy and momentum get all mixed, and okay, you know that the total dimension is going down, but you don't know what's happening to spatial part and the energy part of the momentum space. But on the space-time, you keep having your time that apparently is not affected by the dimensional reduction, and then the dimensional reduction happens on the purely space side, which is something cute, I would say. And with this I conclude.
Good. Thank you.
Thank you.
So coming back to this phenomenological part, okay, at least naively, it looks like this can also kill your theory, right? Because once you allow this guy to fluctuate, then you should take into account the exactly same fluctuation in the, let's say, in correcting the kinetic term of other particles, like standard model particles, let's say neutrino or an electron. But if it will give you a similar coefficient.
Well, it depends on, I mean, you have to assume how this would couple to that.
No, but gravity, this is gravity.
This is not gravity, this is a scalar field. Here I'm doing a scalar field.
So
I'm not assuming, so I don't know what, I'm just doing scalar field in a model where the measure is deformed.
No, I understand. But
and I'm not doing anything else.
No,
if you want to do more, of course, you need to have a more better constructed theory.
No, you said that this is a theory of quantum gravity. That's what you said.
This is a model for quantum gravity. So in quantum gravity, we know that dimensionality, something is happened to dimensionality, And this is
No, I'm just
the
saying that you
simplest way.
compute two loop diagrams in this theory, and you penetrate this breaking to the standard model particles. I don't see how you can avoid it.
No, but here, I mean, here there are no standard model particles. It's this is a toy model, if you want. It's you would have to
But
know.
you understand what I mean?
Yeah, but you would have to know.
You understand my comment? What I'm trying to say?
Yeah, you are saying that the effects of these would propagate
Necessarily, because these
necessarily, but
couples to gravity, and gravity couples to everything
but you
else.
don't know, because gravity might be conformally coupled, and then nothing couples to gravity. So you don't know what's happening at that scale. We don't have a theory of quantum gravity. So
No,
this is not.
then what can
I
you
mean,
do to
what you're
minus
saying
five?
is that, okay, then we have to ask that gravity does not couple to the rest of the particles,
No,
which
sorry.
could be.
No, sorry. Either you admit that there is an issue that I'm raising. You cannot just dismiss. You are telling me.
No, it's not
You are
that.
giving a talk and saying that you have a theory, or at least a model of quantum gravity. I'm trying to be constructive.
No, I don't have a
I
model
mean,
of
I want
quantum
to
gravity.
help you because it's very nice to have phenomenological predictions, and then you are trying to dismiss it. You say,
No. I'm saying that this is not a full theory of quantum gravity. This is a model, a very simple model. It's not a theory for quantum gravity. From what you say, of course, it follows that the full theory will have to couple to gravity in such a way that the effects are not propagated.
Yeah, but I mean,
I mean, it's a big problem. Of course, it's a big problem.
Well, I'm
but
not saying it's a problem. I'm saying I didn't compute it. I'm just saying on the first reaction, I think there is a very interesting thing. You could just, even after this talk, sit down and estimate. And maybe you can tell me that there is no problem, that the suppression.
Yeah, I don't know. I don't know, because I didn't write down the
two loop
full.
factor, will be this factor, stuff like that. It's a very interesting phenomenological question. And instead you are trying to say, no.
No, I don't want to say that it's not interesting. It's super interesting. It's
most
just that.
interesting part in this is that you can predict something. That's why you are showing this 10 to minus 5, right? That's what I'm saying.
Yeah, sure. No, the issue is there, of course.
Hold on.
You have two momenta basis. In one basis, you have just the usual Klein-Gordon form of the mass shell, but the measure is non-trivial. In other, is opposite. I mean, so in both, can you tell me how you add the momenta in this basis in which you have just a trivial measure? I mean the standard measure. Because you said it's complicated.
No, so for
when you have a mass shell, Klein-Gordon mass shell, but in the other case, what is the addition law? Is it abelian or non-abelian?
So you start from one base. So you're talking about the kappa Poincaré case, I guess.
No, I'm talking about your talk. I mean, because you are writing P plus Q. I mean, so what does it mean P plus Q in this basis where you have just this complicated Casimir? Is it just kappa Poincaré?
So the issue of the addition is relevant in the kappa Poincaré, because there it's where you need to modify the addition to be relativistic. In the other cases that I have considered, they are Lorentz breaking. So I just consider standard addition rule, and that's not a problem.
So you just change the p variable, yeah?
Yeah.
Okay.
In the other cases,
okay.
Yes.
So if you have your addition law the same as in the kappa Poincaré, so there is a whole bunch of papers. Even there are papers about the quantized free fields, where you have really done everything rigorously with the covariance under kappa Poincaré. So this is a kind of poor copy of these things which we do in kappa Poincaré.
Everything
Okay?
is a copy.
Okay, because you just, I mean, the thing which you did here is just to go to the coordinate system, which of course is also considered for kappa Poincaré systems. It means it calls so-called free bases, in which you have just the classical Poincaré algebra, and of course you have all these things has been calculated. But I think the fields, of course, you obtain by the change of variables, and you need for your Hausdorff dimensions. So this point is just I would say, for me, say just an element which is original in this stuff.
So
the rest
the
is a kind
quantization
of,
in kappa Poincaré has been studied
no,
already.
the rest. I mean, if you would look at the for example, papers on fields which are a kind of free fields.
So one example where this has been done is this paper, and I'm sure there are other works on that in the kappa Poincaré.
This is the first paper in Rome which has been discussed. This I can comment like this.
Okay. Good. short, and the answer is going to be even shorter.
Okay, yeah. So,
So a yes, no question.
Look, I'll just go back to what I said exactly with draw case. Namely, if you look at the amplitude of the spectrum, it's LP over lambda squared. And that means that somehow the scale lambda at which this sort of running of the spectral dimension kicks in, it's 10 to the 5. Now, in Planck units. But if you look at Benedetti's graph from 2009, you actually see that the significant rounding occurs only at the Planck scale. Again,
But that's
contradiction. If you take that Benedetti's plot, the face value, then you can actually say your lambda is, let's say, 1 in Planck units, and then the amplitude is 1 in Planck units. And
yeah, so this would, no, this would mean that that specific model there is not compatible with the data.
But
That specific model, then there could be, but that's only one. Yeah, it's one quantum gravity model. There are.
Model. So you say that your calculation moves out the CDT model because it gives you. It gives you large quantum fluctuations without inflation. Of course. Yeah, but without no. But then you just say that you still need inflation to actually, in some sense, inflate the spectrum. I mean,
it's going to be order 1. One scale, which means that's it. You won.
Yeah, this is.
it stays order 1.
In that case, it would probably stay, and this would tell you that that model is not a viable model,
Okay,
or at least.
tell me which one is.
I don't know. I wish I knew. I would get a Nobel Prize now. It's
So